Welcome to the discussion on this topic, volumetric strain. This is a part of the unit 1, namely stresses and strains in strength of materials 1 course. This is a continuous topic after the Hooke's law topic was discussed. So what are the intended learning outcomes at the end of the class that I hope that everybody can get is relate to the stress strain relations in one dimensional, two dimensional and three dimensional space of bodies. Also the concept of volumetric strain, right? Now if you look at the three-dimensional space state of stress where only axial forces are acting. So when you consider the three-dimensional state of stress, there will be shear stresses are also acting, but here we are considering only axial state of stress. So when there is an axial state of stress acting like this in all the three directions, there are normal stresses acting perpendicular to this particular area or normal to this area. This is a stress acting, so that is sigma x. Normal to this area, this is a stress acting, that is sigma y. Normal to this area, this is a stress acting, this is normal stress in the z direction, normal stress in the y direction, and normal stress in the x direction. So since they are they are either can be called as normal stresses, or you can even call it as axial stress when you consider the x direction. This is the axial force and axial stress or force in this direction, and this is the axial stress in y direction, the axial stress in z direction. Having no understanding the three-dimensional state of stress, now what we will do is to get better understanding, we will go the strain calculations direction by direction, one after the other. Let us consider the x dimensional x dimension, right? X direction. So if you consider the x direction, the stress acting here is sigma x. So when x direction is considered, this is the black, this is the stress acting here. So the strain that is developed because of this axial stress, or even you can call as a direct stress or normal stress, right? You can call any one of these names. The strain developed, right? This is according to the Hooke's law, right? Hooke's law states that stress and strain are proportional to each other within the elastic limit. So when you remove that elastic limit, we are getting this proportionality constant, and that we are calling as the Young's modulus or modulus of elasticity. So here epsilon x we can directly get, right, from the stress acting when we divide the stress with the Young's modulus. So this is purely as per the Hooke's law, right? Now we also studied in the previous class about the Poisson's ratio, right? The Poisson effect or Poisson's ratio we have seen, right? The Poisson ratio relates both lateral and longitudinal strain. So when the stress is acting in this direction becomes the longitudinal direction. The other two, namely this direction or the depth direction, width or depth direction, they becomes your lateral directions. In other words, when the stress is acting in x direction, y and z becomes your lateral directions. So the Poisson's ratio connect both the lateral strains and longitudinal strains. So if you know the longitudinal strain, automatically you can get the longitudinal strains, that is epsilon y and epsilon z, using the Poisson's ratio. So epsilon y is nothing but minus of this, because Poisson's ratio is negative of the lateral by longitudinal strain. So from this definition you will be getting your strain in y direction. Lateral strain in y direction is nothing but minus mu times epsilon x, where epsilon x is already calculated from the Hooke's law. Now you will be getting minus mu times epsilon x. So that is equal to minus mu times, when you substitute for epsilon x, you will be getting this particular relation, minus mu times sigma x by E, and your lateral strain in z direction due to the longitudinal stress in the x direction is given by epsilon z equal to minus mu times epsilon x, right? So there, because of this extension, there will be a contraction y and z direction. That is what we are calling as a Poisson effect. So from that particular concept of Poisson effect, we are able to get the values of strains in the other two lateral directions. The same thing we can extend to the other two directions. That means when I apply stress in the y direction, my lateral directions will become now x and z. So you can see that here I am applying the stress, direct stress, or you can call longitudinal stress, or you can call normal stress, whatever name you can give. They are all giving longitudinal, axial or longitudinal strains, and the other two directions you will be getting the lateral directions. Because there is extension in y direction, the other two directions get contracted. That means the direction of the if this is the depth direction, the other two length and width directions will become contracted. Now here epsilon y directly can be calculated from the Hooke's law, because the stress is acting in the direction, the strain can be calculated with help of Young's modulus, right? So epsilon y is sigma y by E, and if you want to calculate the lateral strains, you can use the Poisson effect, right, or the concept of Poisson's ratio. There we can be getting minus mu times epsilon y. Therefore you will be getting epsilon x and epsilon z, right? You got epsilon y, epsilon x, epsilon z, right, for the y direction. Same thing you can do for the z direction. You will be getting these particular values, right? So what we have done so far is we have considered direction by direction, and we worked out the corresponding lateral strains and longitudinal strains. So when x direction you have taken, yz becomes your lateral directions or lateral strains, and when you take y direction, x and z becomes your lateral strains, and when you take your z direction, xy becomes your lateral strains, which can be calculated from the effect of Poisson's. Then once you have calculated the all the three strains, right, we can consider the combined effect. So the original state of three-dimensional state of stress is acting, all the three stresses acting at a time, but for the sake of simplicity of understanding, we have taken one direction of the after the another direction. But if you consider all the three states of stress at a single shot, then what happens? All the stresses are acting, so we can sum up them. So when you sum up them, what you will be getting? Epsilon x equal to, when the stress is acting in this direction, x, y and z, then epsilon x will come in all the three cases. When the stress is acting in x direction, there will be epsilon x. Maybe it is kind of extension, the other two becomes contraction. So epsilon x is equal to epsilon x by E, which we have calculated previously, right? Epsilon x equal to sigma x by E, and now then the other two places where we got epsilon x, when the stress is acting in y and z direction, there also we got epsilon x, and here again epsilon x. If you sum them all, then you will be getting epsilon x for the three-dimensional state of axial stress system. So epsilon x by E on the other two direction, minus mu by E times sigma y plus sigma z. Similarly, you can get in y and z directions, right? So these are the equations for a generalized Hooke's law, right? In three dimensions, if you consider all the three dimensions, the axial stress is acting on the three directions. These are the strain values. The strain in x direction is given by this formula, the strain in y direction is given by this formula, and the strain in z direction, is given by this formula. Now comes to the topic of volumetric strain. So how the volume, when a particular body is subjected to some kind of axial forces, or even a combined state of stress system, there will be some volume changes that the particular body is undergoing. So how to calculate those volume changes, right? So we will call the change in volume as the uh, improvement, or you can say increase or the decrease in the volume. You can refer it as a change in the volume. For example, if you consider a particular a rectangular block such as this, it has L, and the length is L, B is the width, and D is the depth. In that situation, we can refer it its volume as LBD, right? Length, breadth, and depth. And if you want to calculate the increase in the volume, what you are supposed to do, whatever the new changes happen in the dimensions of the body, if you can simply multiply them, you will be getting the increase in the volume, right? L becomes L plus delta L, and B becomes B plus delta B, and D becomes delta D, and summing them, you will be getting, if you multiply this and simplify this, you will be getting these LBD terms, and delta L times BD, and delta B times LD, and delta D times LB, and you will be getting other terms such as L times delta B delta D, right? Delta B, these are all referred as here as lower order terms. You can ignore them. The reason is already delta is very small value, right? So when you multiply with another delta, it becomes negligible quantity. In that sense, we are ignoring such minute values. So if we ignore that, you will be getting only up to this. These are the increase in the volume, right? Ignoring the lower order terms or negligible quantities, right? Then if you want to get the change in the volume, whatever the new volume you are occurred, V plus delta V minus V, then what will be getting? You will be getting delta V, because here original volume is LBD. So from this V plus delta V, you will be removing this LBD. So you will be left with this term, delta L times BD, and delta B times LD, delta D times LB. So this is your change in the volume, right? Now if I want to get the volumetric strain, which by definition it is no change in the volume to the original volume. So change in the volume is delta L BD, this quantity we have worked out, and if is divided with the total volume, your equation turns to be, because this BD get cancelled here, delta L by L you will be getting, and here delta B by B you are getting, and delta D by D you are getting here, and thereby you will be referring this delta L by L as your epsilon x, because change in the length by original length can be treated as a no, this is x direction, right? So strain in x direction, strain in y direction, strain in z direction, that what we have calculated earlier, epsilon x, epsilon y, and epsilon z. So these terms will be coming here, right? As so your change in the volume, or volumetric strain is nothing but summation of all the three strains in each direction, epsilon x, x direction, y direction, z direction, right? So you will be getting the summation of this term, and this term, when you will be getting like this. So if you simplify this, you will be getting no here you can take 1 by e common, you will be getting sigma x, sigma y, and sigma z, and again from here you will be, if you take common, you will be getting mu by e times 2 sigma x, 2 sigma y, and 2 sigma z. So from the entire equation, if you take common, sigma x, sigma y, sigma z is present in the both the terms. So your final equation turns to be like this: epsilon x plus epsilon y plus epsilon z by e into 1 minus 2 mu. So this is your formulation for the volumetric strain. Epsilon v is equal to sigma x plus sigma y plus sigma z by e times 1 minus 2 mu. Here we have to mention the if here we have only considered the axial stresses. So one may get a question here: what happens when there are shear stresses combining acting along with the axial stresses? But here we should know that the shear stresses have no influence on the axial what you call longitudinal or axial strains, right? So for an isotropic material, shear stress will produce only corresponding shear strain. So shear stress results in shear strain, but it will not affect on this in this case. They will not affect the axial strains. So thus we are getting, if you want to get the shear strain, that is quite no, with the help of again Hookes law, right? We can get this wall shear modulus, shear stress by shear modulus. So if you want to get in gamma x, where gamma is shear strain, xy gamma x y results to tau xy by g, and similarly you will be getting gamma yz and gamma zx. You will be getting tau yz by g, where g is nothing but your shear modulus, right? This can be given with the different symbols like G or C or N. Different textbooks are showing different symbols for this. So these are the equations from we have no, there we got 1 2 3 equations, right? In the no, these are the equations we got, and here we got other set of equations. They are called constitutive equations for the linear elastic isotropic materials, right? So this is about the topic on of the volumetric strain, right, which is discussed right after the Hookes law, right? That's all about this topic. Thank you very much.